Welcome to this comprehensive course. We are kicking off with Module 1. We'll cover vital statistics and probability. Get ready to build a strong foundation. Don't forget to hit subscribe.
All right, let's just jump right into this explainer. Today, we're giving you the ultimate data detectives toolkit. We're going to take abstract math and translate it into actual real-world business power. So whether you're a product manager, a marketer, or running operations, getting a firm grip on these statistics and probability foundations, it's going to completely change how you make decisions.
Now, think about this for a second. Why do massive companies, with all their resources, still lose millions of dollars acting on data that is technically 100% mathematically accurate? Well, the answer comes down to this fatal gap between doing the math right and interpreting the business reality wrong. Because, numbers don't lie, but man, they can seriously mislead you if you don't know exactly what you're looking at.
So to close that gap, here is our roadmap for today. 1. Describing your data. 2. The shape of data. 3. Inferring the big picture. 4. Testing your hypotheses. And 5. Correlation versus causation.
Okay, Section 1, Describing your data, the first lens. Let's get right into it.
Right, so before you can predict the future, you absolutely have to describe what's sitting right in front of you. That is descriptive statistics. It summarizes the main features of your data set. Basically, it tells you where the center of your data is, how spread out it is, and if it's kind of lopsided in one direction or another.
Now, the most common way we find that center is the mean, median, and mode. But watch out because there's a huge trap here. Imagine you're a retailer looking at average customer order values. If you use the mean, the standard arithmetic average, just a couple of massive corporate orders will completely skew your data upward. It'll make it look like your everyday customer spends way more than they actually do. So the median, the exact middle value when sorted, is a much safer bet because it's totally robust to those crazy outliers.
And sure, these formulas are humming along in the background of your software and spreadsheets, but the absolutely crucial point isn't the math itself, it's knowing which one actually represents your customer's typical behavior. Picking the wrong center point? That's step 1 in making a brilliantly calculated yet completely disastrous business decision.
But hey, the center isn't everything. We also have to look at the spread and the skewness. A positive skew means you've got a long tail to the right, like those few massive orders we just talked about. We also use variance and standard deviation to measure spread. Think about an operations team. Standard deviation is literally their early warning system for wildly unpredictable delivery times. If your spread is huge, that signals a severe process problem you absolutely have to fix before you even think about scaling.
Moving right along to Section 2, the shape of data, finding the fit.
Okay, the majestic normal distribution, the famous bell curve. This symmetrical curve is the foundation of so much statistical modeling because it governs countless phenomena, from human heights to aggregating massive volumes of retail sales. When you operate at scale, it's wild how much of the world naturally falls into this predictable shape.
And here is the golden rule for normal distributions, the 68-95-99.7 rule. This means 68% of your values fall within one standard deviation of the mean, 95% within 2, and a massive 99.7% of all your data falls within just 3 standard deviations. If you're running a manufacturing plant, this sets your ultimate tolerance range for quality control. Anything outside of 3 standard deviations is an extreme anomaly.
But, as we know, the world isn't always a perfect bell curve. Say you manage a call center and you need to predict hourly staffing needs. You're going to use the Poisson distribution, which specifically models rare, independent events happening over a fixed time frame. Or if you're a marketing team predicting yes or no ad conversions, you'd pivot to the binomial distribution. Basically, the shape of your reality dictates the tool you use. All right, Section 3, Inferring the big picture, from sample to population.
So, how do we draw massive conclusions without measuring every single person on Earth? Simple, sampling. Let's say your app has 2 million monthly active users. Surveying all of them? Way too expensive and slow. Simple random sampling works, but to be really safe, we use techniques like stratified sampling. This ensures we pull a perfectly representative smaller group by proportionally preserving all our key user subgroups. It practically eliminates bias right from the start.
And this is where the magic of the central limit theorem comes in. Even if your underlying user data is totally weird and non-normal, if you take a large enough sample, the averages of those samples will actually form a normal bell curve. This lets us calculate a confidence interval, which gives leadership an honest range. So instead of saying user satisfaction is exactly 4.2, which is dangerously precise, you can say it's 4.2 plus or minus 0.15. It gives your decision makers an honest sense of the uncertainty before they greenlight a major rollout.
Now, take a second to think about this quick check. Does that central limit theorem reliably kick in if your sample size is only 25? Well, actually, no. The generally accepted magic number for this to work is a sample size of 30 or more. Any less than 30, and your inferred big picture might be completely distorted.
Okay, let's jump to Section 4, Testing Your Hypotheses, Proving Your Case.
You know, in business, it is incredibly easy to see a metric jump up and just get super excited. But to avoid chasing random noise, we have to calculate a p-value. This tests against the null hypothesis, which is the boring default assumption that your shiny new strategy actually had zero effect. Generally, we want a p-value under 0.05. That simply means there's less than a 5% chance your exciting new finding was just a total statistical fluke.
And you can think of this matrix right here as your ultimate testing cheat sheet. You use a z-test when you have big data and a known variance, like comparing average order values to a massive historical baseline. You pivot to a t-test for smaller cohorts where that variance is unknown. And you use a chi-square test when you're mapping categorical things, like trying to see if there's a real link between a customer's geographic region and the type of product they buy.
Let's see how this plays out in the wild with A/B testing. Say an e-commerce team is testing a green checkout button against a blue one. Listen, they absolutely cannot just pick the one with the slightly higher raw conversion rate. That tiny difference could literally just be random traffic noise for that specific day. Running a proper A/B test with a mathematically calculated p-value, that is what actually protects your revenue at scale, ensuring you only roll out changes that definitively drive positive action.
Which brings us to our final section. Section 5, Correlation versus Causation, Discovering the Truth.
First up, measuring correlation, how two variables move together. For standard continuous linear relationships, we use the Pearson coefficient. It goes from -1 to +1. But here's the catch. Pearson is super sensitive to outliers. So if your data is nonlinear, uses ranked data, or has those extreme outliers we talked about earlier, you need to swap over to the Spearman rank correlation.
But guys, here is the ultimate trap. Correlation just means two variables moved together in the past. Causation means one variable physically directly forced the other to change. It is incredibly tempting for a marketing team to see that people who open more emails also spend more money and just automatically assume, hey, sending more emails causes more spending.
But they might be missing a massive confounding variable. Highly engaged, already loyal customers just do both. They open emails and they buy things. Blasting spam to an unengaged user is not going to magically make them buy. It's exactly like how summer heat acts as a confounding variable that causes both ice cream sales and tragic drowning incidents to spike at the same time. They correlate perfectly on a graph, but obviously, buying an ice cream cone does not cause a drowning.
So, I want to leave you with this final critical thought for this explainer. If historical correlation isn't enough, how do we actually find the truth? Well, observational data is never going to be enough. The absolute only reliable way to establish true causation is through a properly controlled, randomized experiment. By randomly isolating variables, you strip away all that coincidence and confounding noise. And that is exactly how you stop guessing, start proving, and truly become a master data detective. Thanks for joining